Higher Notes, Unit 1, Section 4, Collisions and Explosions. This is part 3, where we look at energy in collisions. Well, so far we've considered various collisions before and after the collision, which is what we must always do. Let's just use one more example. Let's imagine two railway carriages colliding. So here's number one. We'll call that M1 with a mass of 4 times 10 to the 4 kilograms, let's say. And he's travelling in at 3 meters per second. And he bangs in to another railway wagon. Let's give that a mass of 2 times 10 to the 4 kilograms, which is originally at rest. Okay. We'll assume that they join together, as railway wagons usually do. And move off with a common velocity, which we'll call v. Okay. So, let's work out the common velocity using our standard conservation of momentum approach. And then we'll have a look at the energy in this situation. So momentum first. So we can always say, because it's universally true, that no matter what happens, the total momentum before will always equal the total momentum after. So, in fact, irrespective of what happens with energy, the law of conservation of momentum is always true. You don't need to know anything about the energy to know that the momentum is conserved. So M1 U1 plus M2 U2 equals M1 plus M2 V. Because they couple, they join together, they can only have a common velocity. So 4 times 10 to the 4 times 3, put those in brackets, plus 0 equals 4 times 10 to the 4 plus 2 times 10 to the 4 times the unknown v. So our left-hand side then becomes 12 times 10 to the 4 equals 6 times 10 to the 4 times v. So the common velocity is 12 times 10 to the 4 divided by 6 times 10 to the 4. Well, clearly the two 10 to the 4s will cancel. 6 into 12, 2 meters per second. So the carriages, when coupled after the collision, move off at 2 meters per second. Right, so far that's just standard conservation of momentum. Now let's have a look at the energy involved in this interaction. Well, first thing to say is that total energy is conserved. It must be by the law of conservation of energy. Let me emphasize, though, that I'm talking about total energy. So what that means is that the total energy before the collision will always equal the total energy after. Okay. That's basically a statement of the law of conservation of energy, and it takes into account any heat that's generated due to the friction of the interaction and any sound that's given off. You can imagine two railway wagons slamming into each other. There'll be quite a bit of sound, quite a bit of friction, quite a bit of heat. So some of the kinetic energy of the original vehicle will be converted into heat and sound, and therefore not available as kinetic afterwards. So let's do a kinetic energy calculation now and see how that works. So this is kinetic energy we're now interested in. Now the only way to work out what's going on with kinetic energy is to divide up your working into before and after, just as we do with the momentum calculations, really. Well, you know the expression for kinetic energy. It's a half m1 u1 squared. And in this case, because the second vehicle's at rest, it's just 0 for that one. So it's a half. Now the mass of that first one was 4 times 10 to the 4. And he was coming in at 3 meters per second. Don't forget to square the 3. So let's see what we get for that. So all of that turns out to be 1.80 times 10 to the 5 joules. So the incoming wagon has 1.8 times 10 to the 5 joules of purely kinetic energy. Now let's see what we've got after the collision. Well, we've got two bodies moving now, so we've got a half, two bodies coupled and moving, so it's a half into m1 plus m2 v squared. So that's a half into 4 times 10 to the 4 plus 2 times 10 to the 4. And we already know their u speed was 2. Don't forget to square the v. So what does that give us? Well, that's a half times 6 times 10 to the 4 times 2 squared is 4. And that gives us 1.20 times 10 to the 5 joules. Now you can clearly see that we have lost kinetic energy in this interaction. There's only 1.2 times 10 to the 5 joules afterwards, whereas we previously had 1.8. So what is going on? Well, clearly 0.60 times 10 to the 5 joules of energy has been lost in the collision as heat, and in this case there will also be sound. So when, and this is an important sort of definition now then, this is called an inelastic collision, and an inelastic collision is one in which the kinetic energy after the collision is less than before the collision. And the energy that's lost, the kinetic energy that's lost, as we've said above, tends to go to heat and sound. The energy that we're talking about as being lost, of course, was kinetic. It's kinetic energy that's being lost to heat and sound. So that's called an inelastic collision. And a couple of sort of notes on that. Sort of number one, most everyday collisions are inelastic because energy is always lost, usually due to friction, releasing heat. Kinetic energy is lost as heat. And second note here is when the bodies join, the collision will always be inelastic. And again, that's because when they join, there will inevitably be friction, which causes a loss of energy as heat. So that covers inelastic collisions. To finish off this note, we'll say something about elastic collisions, sometimes called perfectly elastic collisions. Well, let's clarify what we mean by that. In an elastic collision, often it's just called elastic rather than perfectly elastic, they mean the same thing. So in an elastic collision, EK before indeed equals EK after. Now these are quite rare, and in practice they only tend to occur at the subatomic level. So elastic collisions only take place at the subatomic level. For example, two protons colliding. They could be going in the same direction, or they could be going in a different direction. So if that was the before, your after might be like this. They both recoil. And because when two protons interact and collide, there's no physical contact. What's basically happening is they repel each other, and so it's their electrostatic fields that basically overlap with each other. So there's no actual friction involved, therefore no energy is lost. And again, to check that it was perfectly elastic, you would have to calculate the total EK before to make sure that it equals the total EK after. You can't just assume a collision is perfectly elastic in an exam situation. You have to actually work out the equations. So you'd have to have a half m1 u1 squared plus a half m2 u2 squared, and check that that adds up to a half m1 v1 squared plus a half m2 v2 squared. Okay, so that would only be the case in a perfectly elastic collision. And as I've said, this really only takes place at the subatomic level. But you must always do the calculations of EK to check that the kinetic energy afterwards either does indeed equal the kinetic energy before in total, or is less than. And that allows you to decide whether it's elastic or inelastic. One final note is that collisions, which are in fact explosions, are always inelastic, because clearly there's no kinetic energy before, but there's lots afterwards, so clearly they can't be elastic, so they are classified as inelastic. And that completes the section on energy in collisions.